Hello everyone, today we are going over concept 5-7, electric potential energy. And I just want to start off by analyzing the relevant equation for calculating electric potential energy, which I've just written out over here. And I want to compare it to the force equation for electric charges. So recall that the force between two electric charges is equal to the k constant times the absolute value, the magnitude of charge 1 times the magnitude of charge 2 divided by the distance squared. So this is an important thing to note because the force does not consider, for electric charges, does not consider positive or negative. Force is always positive between two electric charges, regardless of their charge. So we could have a positive and negative, negative and negative, or a positive and positive. And if they were equal distances with equal charges, they would have the same force between them. However, when we approach the potential energy equation, we see that, the electric potential energy equation, we see that there are no longer these absolute values around the charges, meaning that you can have negative potential energy between two charges. And also consider that the distance is no longer squared. R is no longer squared here, meaning that the relationship between the electric potential energy and the distance is inverse, but 1-to-1. So if the distance were to decrease by a factor of 2, so if it were to decrease by a factor of 2, the electric potential energy increases by only a factor of 4, or only by a factor of 2. In contrast, if you were to decrease the distance between two charges by a factor of 2 when considering the forces, so let's say that decreases by a factor of 2, the force between those two objects would increase by a factor of 4. So those two considerations are important to keep in mind so that you don't mix up these two equations. You have to remember that these two equations are noting different distances or different relationships between the distance, and that they don't consider the magnitude. So the electric potential energy does not consider the magnitude of the charge. It simply considers the charge itself. So it can be negative or positive. And another thing I want to note is related to this graph here. So let me just draw again. We see that for like charges, so positive and positive or negative and negative, when the charges are very close to each other, they have a high potential energy. And as they get farther apart, their potential energy continues to decrease. And it's asymptotic around 0. So it'll continue to decrease, but it'll never touch a 0 until they're infinitely apart from it. They have an infinite distance apart from one another. In contrast, when you have like charge or opposite charges, so a positive and a negative or a negative and a positive, we see that when they are super close together, so if they were just touching, they have an infinitely large negative potential energy. So as they get farther apart, their potential energy actually increases, but it never reaches 0. So it's going from more negative to less negative. And that's an important distinction because this is technically increasing the potential energy as they get farther apart. Whereas when you have two like charges, the potential energy decreases as they get farther apart. So with that in mind, let's get started on these questions. So 5-7 quiz question 1 states, which of the following is true about the electric potential energy of one positive and one negative charge? If there is more than one, you must select all of them. So answer choice A says that the electric potential energy between the two charges is positive. B says it's negative. C says it increases as the charges move farther apart. D says it decreases as the charges move farther apart. And E says it gets closer to 0 as the charges are moved farther apart. So this is based on the graph that we just analyzed. And we can see that for two opposite charges, that the ones that they're asking us to analyze, we see that when they're very close together, the electric potential energy is highly negative. So it's in this negative quadrant of the graph. So it's highly negative. And as they move farther apart, the electric potential energy becomes less negative. And the way I want you to think of this is in terms of, like, let's say debt. If you go from $100 of debt to only $10 of debt, you are getting less in debt, but you are increasing your overall wealth. So we can't say that our wealth is decreasing because the debt is decreasing. We're saying that our wealth is increasing because we have less debt. In a similar vein, as the negative potential energy decreases, we are gaining potential energy. So it is as these two particles are moved farther apart, the potential energy actually increases. It does not decrease. And that's because we're going from something that's highly negative to something that's very close to zero in terms of the amount of negative potential energy. So it increases overall. And finally, as we can see, as these two particles are moved infinitely farther apart, they approach the x-axis, which would be zero. Meaning that as the two particles are moved farther apart, they approach zero potential energy. So with all of this in mind, we can say that for two opposite charges, the electric potential energy is negative. It increases as the charges are moved farther apart, and it gets closer to zero as the charges are moved farther apart. So A and D are false, but B, C, and E are all true. For 5-7a, this question is simply asking us which one of these three systems has the greatest electrical potential energy. And we see that they have like charges, so if we recall this graph, potential energy becomes more positive as they become closer together. So since it's asking us for which one has the largest potential energy, it would be the one that has the highest value of potential energy. So with that in mind, let's just write out a qualitative version of the equation U equals K times Q1 times Q2 over R for each of these. So we already wrote the first one because charge 1, so this is 1, this is 2, and this is 3, and I'll say this is 1 here. So for system 1, we have the electric potential energy is equal to the K constant times charge 1, which is, let's just denote it as 1 charge, 1Q, times charge 2, which is also denoted by 1Q, divided by distance R. So that is all noted in the equation for number 1. Moving along to number 2 here, I'm going to write it over here. So 2, the electric potential energy is equal to K, so the K constant is always the same, times, we still have this Q charge here, which is 1Q, so 1Q, times, now the charge on the second, the magnitude of the second charge is 2Q, divided by 2R. And 2 divided by 2 is simply 1, so we can say this simplifies to U equals K Q1 times Q2 over R, which is the same as number 1. So let's consider the third one now. Let's write out the equation for the third one. We see that U is equal to K, the K constant, times the charge that's still the same as the first two cases, so Q1, times this charge here that's equal to 4Q, so times 4Q, divided by 2R. So 4 divided by 2 now is equal to 2. So we can simplify this equation and say that U is equal to K times 2Q1 times Q2 over R. And if we compare this equation to the first two, the simplified versions of the first two, we see that the third system has twice the electrical potential energy as the first two systems, meaning that C is the correct answer. And the other two are false because they are, the other two are not the correct answer because they have less qualitative electrical potential energy. So A is false, B is false, and D and E are false because the middle one has less electrical potential energy compared to the last scenario, and the first two have overall less electrical potential energy compared to the third one, meaning that C is true. So this is going to be a short video because this is the last question we have, 5-7b. When a negative charge, negative Q, is released from rest near a second fixed positive charge, Q plus Q, what happens to the electric potential energy of the pair of charges? So let's recall that opposite charges attract. So we have this test charge here, and I'm going to draw a line underneath it to denote that it's fixed. And we have some negative charge Q. Negative charge Q here, and then this is big Q. So this is negative Q. And it's asking us what will happen to the electric potential energy of the pair of charges. So this is relying on our knowledge of that chart that we showed at the beginning of the video. Specifically, opposite charges are in the negative quadrant, and as they get closer together, the electric potential energy decreases. So I'm going to erase that arrow there. So we're saying as these two, we're saying, one, what is happening to the distance between these two charges, and then two, what is happening to the electric potential energy of these two charges. So we know that opposite charges attract, so they'd be getting closer together. So if we're looking at our answer choices, B and C are false because they're saying that the opposite charges would move away from one another, but that's not true. These are opposite charges. They are attracted to one another, so they would move toward one another. And then using this qualitative version of the graph that we saw here, we see that as they get closer together, the electrical potential energy decreases. It becomes more negative. So between answer choices A and D is true because A is saying it will increase because Q will move toward, negative Q will move toward positive Q. But that is just simply not the case, because if we just analyze this graph that we showed at the beginning of the video, this one right here, we see that as these two opposite charges get closer and closer together, the electrical potential energy infinitely decreases. It infinitely becomes less positive. So because of this, D is the answer, and E is also false because we have enough information to tell what will happen to these two charges. So that is the last question we have for this video. Thank you so much for watching. Hopefully you enjoyed. If you did, please leave a like on this video, and have a great day.